Swayam Prabha. Digital India. Educated India.
Let's recap the read graph definition, right. So we said that we want to take the connectivity of the level sets and we care only about the number of connected components, right. So, this is a very simple form of topology, right. So, the simplest form, and we are saying every connected component shrinks to a point, right, and then you kind of glue these points together, right. This gives you a graph, right. This graph is called the Reeb graph, and formally this is the quotient space of the domain that is given by the equivalence relation, right. Okay. So, it is important to understand now the connection between changes in topology and the different types of critical points, right. We know already that there is a relationship. We will study this a little bit more carefully now. Regular points are what people usually study a lot, but in this case regular points are not so important. We will discard them quickly, right. So, this is where no topology changes happen, right. So, if you look at the local picture for a regular point, so by the way all the examples that I give initially will be for initially 1D then 2D, right. So, 1D contours and then 2D surfaces, right. So, remember 1D contours appear in 2D functions, right. Iso contours appear in 2D functions, iso surfaces appear for 3D functions, right. Okay. So, so these examples are so a regular point, the point in the middle is a regular point, and what I am going to show you is before and after pictures, right. So, before I pass through the regular point and after I pass through the regular point, in solid I am going to show you the iso contour. The center will be the point and the blue disk with the dotted boundary is the neighborhood of this point, right. So, you can clearly see that the topology of the iso contour does not change, right, before and after, left to right. Now, let us look at this picture for critical points. These are the interesting things, right. So, this is even one dimension lower, 1D. So, what will be the level sets? They will be points now, right. So, what about the minimum? The dotted is the domain and you are looking at the minimum. The before picture is empty, there is no iso point before you hit the minimum, right, makes sense. After you hit the minimum, there are two iso points. So, if again if something is not clear, please ask me so that we can clarify that before we go forward. Next, maximum. Once you understand minimum, the maximum it becomes easy. The before picture is you have two iso points. So, remember here the function, the height function is what we are using, right. So, before two iso points, after is none, right. Okay. How about now the local pictures for critical points 2D functions? Minimum again, before picture is empty as usual, after picture is you have one component again, right, one component of iso contour, right. Remember if you go try to recall what you saw with the sphere and the torus, there was one component. What about the maximum? Before you have one component, after you have 0 components. So, the one component dies. How about the saddle? This things get interesting now. The saddle as you go, as you are before, let us assume that there were two components, right. So, again remember the blue region, the circular region is a local neighborhood. The solid line is the iso contour within that local neighborhood and you are looking at the neighborhood of a saddle now. So, before you hit the saddle, you have two components, right. So, saddle again try to imagine the horse's saddle, right. You are sitting on the horse, right. So, in one direction the function is going down, in another direction it is going up, right. So, the down direction is where you have two contours, two components, right. Just look at the neighborhood for now, just look at the blue neighborhood for now. What happens after? It is still two components, it seems like, right. So, it is not sufficient to look at the local neighborhood, you have to see how these level sets are connected globally. So, you have to look outside the blue circle, outside the blue disk, right. So, if you look at this guy, the above, globally how is it connected? The two components actually are globally connected into one closed isocontour, right. So, that is the dashed lines that shows how the isocontour is connected globally, right. So, if the isocontour is connected globally, then after you pass the saddle, it breaks into two. Does that make sense? It breaks into two components. Now, imagine in contrast, if the same local picture, there is no difference between the local pictures here. The local pictures are the same here, right. So, this local picture is the same as this local picture. It is no difference, right. Again you have two components, right. But what is different is how the isocontour is connected globally. In this case, it is connected globally into a single connected component. Here it is connected so that it forms two different connected components, right. Now, what happens in the other case? They were actually two different components globally. Then after you pass the saddle, this gets connected into one, right. Remember, this is what we saw in the torus example. The saddle was where two components merged into one or one component split into two, right. So, this is all that can happen at a saddle. Two components can merge into one or one component can split into two. So, the summary is that when you pass a critical value, right, the topology of the level set changes, either by increasing number of connected components or by decreasing number of connected components. So, if you understand the 2D picture, the 3D should also be simple in terms of what you expect. Of course, the details will be a little bit different. Let us look at the minimum first, right. So, minimum is kind of easy, right. Before picture is empty, after picture is where you have one connected component. What is the iso surface now? It is the sphere, and the before picture for the maximum is again a sphere which gets deleted or vanishes after you pass the maximum. Now, the saddle becomes interesting. Again, what we are seeing here in blue is only the local isosurface, the isosurface in a local neighborhood. We do not know how it is connected globally, but we know that if this is the local isosurface, it gets connected like this after passing. So, if globally this guy was connected like that, so two spheres, right, then what happens here? So, after passing the saddle, this guy will, the two components will merge into one. There is no difference here, right. So, this is also a sphere, it is a deformed sphere, imagine that, right, it is just a deformed sphere. I will just try to draw it on the side, one component, right, that is the isosurface, it is a deformed sphere, we do not need this. How about the other possibility, right. So, this is the other type of saddle. So, if I call this two saddle, this is the one saddle. So, in this saddle, the before picture actually looks like this hourglass picture, right, and it really depends how this guy is connected, right. Again, if this is connected like this, after you pass the saddle, that one component splits into two. So, this was the same as the 2D case. So, there was no issues, right. Now, something else can happen. This is what makes things interesting, right. Now, here remember what we said was we had two caps here. What if these two guys were connected like this? Right? If they were actually connected like that, what happens after you pass the saddle? It is already one component. After you pass the saddle also it is a single component, but what happens to it? It becomes like a torus. So, the topology changes again, but the topology changes in a different way. There is a hole that is formed now suddenly, it goes from being a sphere to a torus. The number of components does not change, but it becomes a torus. Right. This change is not captured in the Reeb graph. We do not capture this change in the Reeb graph. We only capture changes in number of connected components. Okay. So, this is a crucial difference. Right. So, right. So, with that let us look at, so again this holds. So, with that let us start looking at the Reeb graph more and understand it better. So, the one thing we know is what are the nodes of the Reeb graph. Each node corresponds to a critical point. Make sense? Now, what are the arcs? What do they correspond to? What are the arcs in the Reeb graph? Right? The arcs actually correspond to a collection of level sets. We know that all these level sets have the same topology because they are all regular points corresponding to regular points. They are all having the same topology. And let us look at this pictorially. Right? So, as I sweep this domain with increasing function values, you see that the topology changes at different places, the same kinds. There are saddles where the number of components merges or splits. Right? Now, I have color coded the arcs. The exact color is not important. If you can distinguish the different colors, that is sufficient. Imagine what will be the part of the domain corresponding to each arc. Right? So, this is what you will get. So, these are in this cylinders, we call them cylinders. Right? These are collections of level sets. Right? So, for example, let us look at the red one. Right? So, all these level sets have the same topology. They are all disks or circles depending on how the domain is. The same holds for this hourglass cyan cylinder as well. So, every arc here, right, maps to a cylinder here. Right. This is true for all arcs. This is true for this brown arc also. Right. This is true for this small black arc as well. Right. This is important. We will come back to this later. Right. Because this is going to be playing an important role in understanding something about our data. Right. This mapping between arcs and subdomains, right, or cylinders is going to be useful later. So, this is where I wanted to stop, but let us talk about properties now. Right. Let us take the torus which is lying flat on the ground, right, and not upright. What will be the Reeb graph is the question. Now, what do you expect? What is the minimum? If you take the height function, the minimum is actually degenerate. It is the entire set of points. It is the entire set of points which actually the torus lies flat on the ground. So, you will actually get a circle of minima. Right? And as you keep increasing, what will you get? Will it be 2 disks or 1? Right. So, in this case, the Reeb graphs, it seems like the Reeb graph will not have a cycle, right, in the middle. But this is a degenerate function because exactly for the reason that this all the minima were along this circle, right. So, none of them were generic, they were all degenerate critical points. So, we will not look at such functions, and like I said, you can perturb this function just a little bit so that it becomes a Morse function. And how will you perturb it? Think about the height function and perturb it by a small angle, as small as you want, small epsilon, right. And this will already move all the critical points away and you will get a single minimum, right, and then you will get the cycle. Can we construct a Reeb graph for any shape? I think the right question to ask is, for any function, can we think about a Reeb graph, right, or is a Reeb graph defined for any function? The shape is not so important, right. What is important is the function that is defined on that domain, right. So, the Reeb graph, remember, Reeb graph R is always defined for a function, right. It is not defined for a domain, it is defined for a function. What I am telling you is, if you give me a function that is defined on a domain, I can construct the Reeb graph for you, or I can define the Reeb graph for you, right. So, it is defined for all functions. You can take the height function, I am just using that for illustration purposes. You can take other functions as well. You can remember that function which was increasing radially out, that is another function. You can take a sinusoidal function, define it on top of the torus. You can still construct the Reeb graph for that, right. Okay. Right. So, let us talk about surfaces a little bit to introduce some topology. and then talk about properties of the Reeb graph. So, here are different surfaces, right. So, I am going to talk about topology of manifolds, but I am going to give examples in 2D, right, only of surfaces, right. The reason is that there is a very nice result there, it makes sense to talk about that, right. You probably, that is another take home message. So, this is a result about characterizing surfaces. So, when you take surfaces are 2D, you just see them in 3D, but they are inherently 2D objects, right. You take a sphere, it is inherently 2D. Now, the result actually says that the surfaces that you see on the screen, these are all the different types of surfaces that are possible. So, formally what it says is that if you take orientable surfaces, right, so this is another technical term, just means that your surface has a well defined orientation, that is something which is clearly outward and something which is clearly inward. The result says that all these orientable surfaces are fully characterized by their so called genus. So, what this says, so what it says is a surface M can be written as a sphere together with G tori, right. So, G different torus, right. So, you have what you are seeing examples for here is just the 1 torus, 2 torus and 3 torus, and you can keep extending that. So, right. So, these are all the different kinds of surfaces that are possible, none else. Any surface is one of these, belongs to one of these classes is what it is saying, right. Any orientable surface belongs to, S is a sphere, of course you can have just a sphere. A sphere plus a torus gives you again a torus. So, this hash symbol, if you have not seen it, it is called a formal sum, right. You can imagine that you are just fusing the two together. Yeah, if it is linked together, I do not care about that, right. For me that is just two different tori, right, two components. You are saying it is like a link, right, like a chain link. Yeah, so it is a chain link. So, you can move it around. No, that I will call it two different connected components. You cannot jump from one link to the other, right. If you think of this as one link, right, and this as the second, this guy can move inside the other. So, then it is a single component. That is no different from this guy. That is actually not different from this. I do not have so I will refer to you to some book there where you can see why one is the same as the other, right. This link and these are knotted with each other. All I am trying to say is that does not matter. It is the same as this guy. You can actually deform that guy into this without cutting. So, it is an interesting thought exercise, but we will not be able to do that today. Okay, you just take my word for it. So, so this is a characterization, and there is a number associated with each of this surface, which is called the genus, right. It counts these what you see really as holes, right. This is not going to be the same as what we will do later, but the genus actually is counting here this something like this, right. It is counting these guys. Kind of informally, this is what it is counting, right. The Euler characteristic, if you have seen the Euler number, right, or the Euler formula, is related to the Euler characteristic, and the Euler characteristic is defined as 2 minus 2g in this case. If g is the genus, then the Euler characteristic is 2 minus 2g, right. So, for the sphere, the Euler characteristic is 2, and then the Euler characteristic keep decreasing by 2, right, and it is negative for all the other surfaces. So, you can restate this by saying that all orientable surfaces are fully characterized by the Euler characteristic. So, now let us look at Euler characteristic a little bit and the relationship with what we are seeing here, right. The Euler characteristic happens to be a shape invariant, right, because we saw that for surfaces they fully characterize the surfaces. I tell you the Euler characteristic, I tell you it is 0 or minus 2 or minus 4, you know exactly which surface I am talking about. It turns out that even for other higher order, higher dimensional objects, right, spaces, the Euler characteristic is still a nice shape invariant. So, it may not be as powerful in high dimensions, but it is still an invariant. What does that mean? It means that if two spaces are topologically equivalent, right, then their Euler characteristic has to be equal. the statement does not hold the other way. So, the Euler characteristic may be weak. So, two different spaces may have the same Euler characteristic, but why do we introduce it? The reason is that there is a relationship with what we have seen so far, right. The Euler characteristic chi is just the alternating sum of the critical points that we saw, right. There is another formulation, we will not look at this first. Let us look at this formulation. So, the Euler characteristic is equal to the alternating sum of number of critical points. So, here I is the index, the Morse index. I is the Morse index, right. So, what are you counting? Number of minima minus number of saddles plus number of maxima in 2D, right. It is alternating plus or minus, right. So, it turns out that this is also equal to the alternating number of so called K simplices. We will look at that a little bit later. Okay. So, let us look at examples to understand this better, right. Let us take a sphere. So, the Euler characteristic happens to be 2, we know this, right. So, 2 minus 2 g, right. So, g is 0 for the sphere. So, hence this is 2, sorry, 2, right. Can we see the relationship with the number of critical points? We can see that, right. So, let us take a sphere. Remember, I do not care what function you define. You give me any Morse function, define it on the sphere, and you compute this alternating sum, you will always get the Euler characteristic. Let us take the simplest possible function, which is the height function. How many minima, how many maxima, how many saddles? Right. How many saddles? 0 saddles, right. So, you have 1 minus 0 plus 1. Can somebody think of another function that is defined on the sphere? Just the shell, the sphere, some other function. Radially outward, that was for the ball, this is just the sphere, the domain is just 2D, right. Can you think of something else? Can you say that again? Perimeter? Okay, so let's. I don't know if I understand it correctly, but let's think about it, right? So you are saying that the function here is say 0, and then increases maybe, and you want to increase and then decrease. Okay, very good. Okay, so the function has 2 minima here, one here and one here, and it increases, right, away from that. So let's make it simple. It is the distance from these 2 points, right. So these 2 points are natural minima, right. There will be some maxima, right. Now which points will be maximum? There will be some point along the equator, right. Let us make it a Morse function. Let us not have all the points with equal function value. Let's think of one of the points as a maximum, right. That is the point which is equidistant from both the points and farthest away, right. Now, what this is saying is, what this result is saying is, this chi is number of minima 2, we have number of maximum is 1. So, what does that tell you about the saddles that should be there? This is saying that there should be a saddle, right. And that saddle will happen to be somewhere here, somewhere in the middle, right. So, these guys will merge here and this, right. So, if you try to draw the contours, right, let us draw it here again. If you try to draw contours, right, from these points, these 2 contours will merge where? At that saddle, and after that they will become one component and die at the maximum, right. So, hence you will get again the Euler characteristic is equal to 2, right. Now, what about the Euler characteristic for a torus? We saw it is 0, right. So, does this match with what we saw for the height function? So, remember the height function on the torus, number of minimum was 1, right, only one minimum. There were 2 saddles and 1 maximum. So, this was again 0, right. So, it matches with what we are seeing here, right. Okay. So, double torus, this is -2 and so on, right. Okay, fine. So, so that was a quick introduction to some of the so the Euler characteristic and how it connects to the number of critical points, right. Now, of course, with once you have the Reeb graph, you actually have the counts of number of critical points, number of arcs and so on. Let us study a few properties about the graph itself, about the Reeb graph itself. We already saw that the nodes can either be minima, they can be saddles, or they can be maxima, right. What will be the degree of the nodes here, right. So, what will be the degree of minima and maxima? They will be 1, they have to be leaves, right, because the number of components either increases from 0 to 1 or goes from 1 to 0, right. So, those are exactly the nodes with degree 1. The saddles will have degree 3 because the number of components either decreases by 1. So, 2 components merge into 1 or 1 splits into 2. So, right, in either case the degree is 3, right, and there are no other nodes in the Reeb graph. So, this is a graph with node degree either 1 or 3, right. Now, in practice we also talk about something called an augmented Reeb graph, where we insert the regular points, right. So, if you insert the regular points, let us say I take a very simple Reeb graph with 1 minimum and 1 maximum, right. The regular points will lie in the arc, in the interior of these arcs, and their degrees will naturally be 2, right. So, this graph is called the augmented Reeb graph. Okay. This is called the augmented Reeb graph. Okay. Right. Now, let us talk about the connection. Yeah, okay. In this case, I did not have any, but let us look at the graph, the Reeb graph that we saw for the torus, right. This is 3. Okay. So, let us take this example. So, remember that this was the Reeb graph for the torus with the height function. This is the torus, right. The critical points were the nodes, right. What were the arcs? They were collections of isocontours that came from here, like that, right. Now, all the regular points lie between a pair of critical points, right, in terms of the function value, right. They will appear, or they will also appear on the Reeb graph somewhere, right. They are not explicitly represented. You take every regular point, it will map to exactly one point in the Reeb graph, and it will be in the interior of a arc, right. So, if I pick a regular point here, this guy will map to some point in this arc, right. It is a unique map, and so it will map to a point, and naturally that point will have degree 2. So, if you declare that point also as a node in the graph, the number of arcs increases by 1 and the number of nodes also increases by 1. So, this new graph where you insert the regular points is called the augmented Reeb graph, right. So, what is the benefit of the augmented Reeb graph? It allows you to take this map back from the graph to your domain.
So, augmented points are not critical points.
Say that again, please.
Augmented points are not critical.
No, the augmented points are not critical points. The critical points will already appear in the Reeb graph. The benefit of including the augmented, doing the augmentation is that you can now go from the arc into the domain, because you know exactly the regular points that this arc corresponds to, right. So the augmentation helps with constructing that inverse map back into the domain. Okay. So now a little bit about other properties of the graph, right. We know what the nodes correspond to, what the arcs correspond to, what are the node degrees. How many components will the Reeb graph have? As a graph, how many connected components does it have? So remember that this is a map from the domain, right, using this quotient topology, right. Now, what does it preserve? Every connected component of the iso surface maps to a point, right. So if you have a connected component of the domain, right, and you have a Morse function defined on it, right, all the level sets will be connected to each other. So this entire domain will be mapped to one connected component of the Reeb graph, right. So if you have a single torus and you have a height function, the Reeb graph will have one connected component. You have two tori and you have a function defined over this two tori, right. Then the Reeb graph corresponding to that will be two different components, right. So this is what we are saying here, that the number of connected components of the Reeb graph is equal to the number of connected components of the domain, which is manifold here M, right. The beta 0 is the technical term for this, right. It is called Betti number, and I am not going to talk about it because it has a brown color, right. This is called the 0th Betti number, in fact, right. So the 0th Betti number. Okay. So this is more or less direct, because it follows from the definition, right. The number of connected components is preserved. But how about loops? How many cycles or loops can the Reeb graph have, right? This is an interesting question which is not so trivial to answer, right. So there were questions about how will the Reeb graph be, right, if I tilt it and use a different function, right. We already saw that the number of nodes can change, the number of critical points can change, right. The question is, can the number of cycles change? Can you define a function, a Morse function on the torus such that it has, the Reeb graph has no cycles, right. So it turns out the answer is no, right. And in fact, you have this relation which follows if again from the same argument, right. Beta 1 actually counts the number of cycles, not connected components, it counts the number of cycles or loops, tunnels, right. Remember, we are mapping connected components to connected components, right. So if you have a tunnel, right, in your domain, that tunnel is connected, right, and you are mapping it to some space, right. That space. So if you are taking this, so maybe I draw it again. No, it will also have a cycle. What you are saying is a distance function from some point outside. That will behave exactly like the height function. It will also have a cycle. So I'll give you a proof for it. So, right. Okay. So here, what we are seeing here. So now I'm trying to argue that the number of cycles in the Greeb graph cannot be more than the number of tunnels in your domain. Okay. So, this is what I am trying to argue now, right. This follows kind of more or less straightforward, right. If I have this part of my domain, right, and you think about what it maps to in the Reeb graph, right. So, this has a tunnel, right. So, this has to map either to a tunnel or to a straight line, right, because this entire guy is connected, it has to map to a single connected component. So, either it maps to a cycle in the Reeb graph or it maps to a straight line where the cycle gets squished, right. So, clearly the number of cycles in the Reeb graph has to be smaller than the number of tunnels that you have in the domain, right. Does that make sense? Okay, fine. Now, what it turns out that for 2D, this is actually the argument holds both ways, right. So let us look at it this way, right. So, this is the result that we want to see, but maybe we will we'll try to write it, right. So, how many nodes do we have in your graph? How many nodes do you have in the Reeb graph? It is equal to the number of critical points, right. If I say n1 is the number of degree 1 nodes, right, and n3 is the number of degree 3 nodes, right. How many nodes do we have? N1 plus N3, great, right. Okay. This is the number of nodes. Okay. How many edges? I hear a murmur. Say that again, please. How many edges? 3 and 3 plus n1 over 2. Fine. Okay. So now how many cycles? If I know the number of nodes and the number of edges, you can tell me how many cycles there are, right? How many edges in a tree? Number of nodes minus 1, right? So every additional edge that you insert creates a new cycle, right? So what you want is the number of edges minus number of nodes, right? And there is a 1 factor there, right? So what you really want is, so what happens for a tree? For a tree, the number of nodes minus 1 is the number of edges, right. So what we really want to calculate now is the number of edges minus this number, right. So 3 and 3 plus n1 over 2 minus n1 plus n3 and 1, right. Can somebody calculate that for me? So you have a 3 and 3 over 2 here, and n1 over 2, so you get a minus n1 over 2, and 3 and 3 over 2, so you get an n3 over 2, right, and a plus 1. Is that okay? Is that fine? So I just want to rewrite this as 1 minus that okay? Okay, fine, great. So this is just manipulation. So if I may be doing something wrong here, I'm right. It's difficult to do this here. But if I've not done anything wrong here, can we recognize this expression, right? The number of maxima plus number of minima minus number of saddles. What is that? We saw the alternating sum, right? This is the Euler characteristic, right? So this is equal to 1 minus Euler characteristic over 2, right? And we know that the Euler characteristic is what? 2 minus 2g, right? So if I replace that, this will be 1 and okay. So what we have is that the number of cycles is equal to the genus, right? So the only crucial argument here was about the number of cycles here. So the number of cycles is what? So if I have a tree, right, with let us say 4 nodes, right, I know that it has 3 edges, right. If I have a graph, right, and I have I know it's connected, right, every additional edge on top of that 3 is going to create a new cycle for me, right. So I'm counting that, I'm counting the number of cycles. So I'm counting the excess. So this is number of edges, right. I'm counting the excess number of edges on top of the n minus 1. This is number of nodes minus 1, right. So that's all I'm counting. I'm counting that excess, right. So of course this is a more like from first principles argument. There is a more direct argument using homology groups. We will not talk. I didn't want to introduce that. Right. This is a more direct argument that the number of cycles is equal to genus, right. So what is this true for? This is true for manifolds, okay, 2 manifolds in particular, right, because that's where you have genus and so on, right. But it turns out that something like this holds okay, so I don't know how to erase the whole thing. So what we want is an expression for the number of cycles in your Reeb graph, right. So the argument we saw was something that holds primarily for surfaces, for orientable surfaces, right. So there we saw that the number of cycles is equal to the genus, right. It turns out that something similar to this holds even if you don't have a nice orientable manifold, right. Even if you have a punctured torus, right, you have a boundary, right. So you have a torus, right, and there is a puncture, right. This is a boundary, right. So that's open. That didn't belong to the classification of surfaces. Remember, right. We were looking for only closed surfaces then. So even in this case, one can show that the number of cycles, the loops, is bounded between the genus G and 2G plus H minus 1, where H is the number of boundary components. Okay. So in this case, there is one boundary component, right. So you can say that it is bounded from G to 2G, right. So the number of boundary components significantly increases the number of possible cycles. Okay. But what is interesting is this case the number of cycles or the loops is fixed no matter what function you choose, right. That is a very strong result. Okay. An outcome of all this is that when you have no cycles, you know for sure that your domain is a sphere, right?
Here the bounded component, the example was stated here,
Yeah.
bounded component H, that is the depth of H.
H is the number of boundary components. Here H is equal to 1, G equal to 1, right?
So when that whole is considered, that is 1.
Yeah. So this is whole is actually not part of the domain, right? So what this means is when you have like a sphere, right, or a circle, right, or a higher dimensions, right, equivalent of the sphere, then you know that the number of loops is actually equal to 0. You cannot have a cycle, right, and you work with trees, and in this case you call it a contour tree. Okay. Why contour tree? I will come to that name, right. So, the contour refers to one connected component of a level set. So, we will see a picture, so we will see that again, right. So, in this case it is a tree, and so this is a nice special case that we will look at in a little bit more detail. Okay. Right. So let us look at that. The definitions are still the same, there is no change in definitions. You will just see the tree structure is more apparent here, right. So let us look at a function now. We are going to move away from height functions. So you will have to pay attention to the level set and how it is connected, right. The shape will not matter anymore, right. So let us look at this 2D function. This 2D function is mapped to color. This is how you read the picture. Dark colors correspond to low function values. As you increase the, as you go towards white, you are increasing the function value, right. So the blue dots are the local minima. So A, B and C are local minima, right, and all the corner points L, N, M, J and on the top G, they are all local maxima, right, and the other green points are the saddle points. You can see a few isocontours are shown here. Try to trace beginning from A, right. The isocontours will be having a single component at A, right, and let us assume that B also has a similar scalar value. So, right, at some point of time, so I do not want to use the pen. So, A and B, right. So, there are two contours, one surrounding A and one surrounding B. These two components will merge. Where exactly they merge? They merge at a saddle which is D, right. And then this component, merged component, merges with the isocontour that began at C. Where do they merge? At E, right, and so on. The other green points are where a single connected component split into two, right. So, for example, at F, right, if you look at F, or let us see something simpler, at I, what is the before and after picture? Before picture is like that, after picture it's like that. One component split into two because of the boundary here, right. Okay. So J is in this case I was a saddle, right. Now we are tracking that as we do always into the Reeb graph, right, but we do not have cycles, right, and this is the color code we will use from now on: blue for minima, green for saddles and red for maxima, right. All other properties are the same, we have not changed anything, we have just looked at we are looking now at a special case, that is all, right. Okay. Here is another picture of this. So, where what you are seeing is a sweep over the domain in increasing function values, right. Look at the boundary of this sweep. you will notice that the number of components is changing, right. So, now there is one component soon, and this one component will, now there is one component, this component splits into two, right, and each component will die at the maximum, right. So, this is also the same as your Reeb graph, right. But each connected component, so right now you have two components, each component is referred to as a contour, right. So, each component is individually referred to as a contour, and hence we call this a contour tree. Okay. Right. Now, you can see in this contour tree some arcs are long, some arcs are small, right. And if you remember the video we saw from a while ago, right, the initial tree that was shown there, I will show it again later, right, was very dense. There were a lot of arcs, right, and that is what happens in practice. There will be lots of arcs, you won't have a nice simple tree, right. So, you will need a way to simplify your tree, right. So, we will talk about that now. Right. So, here is a simple example, things are never as simple as this, but it is good for illustration. On the left you see a terrain, right, and we are again using the height function, right. So, the height function has one minimum, one saddle and two maxima, kind of the inverted the picture of the example we saw earlier, right. One of the hills is much smaller than the other, right. So, this hill is at 80, if you can't read it, this is 80, this is at 90 height, right, and this is at 50 height, right. So, one of the hills is much smaller than the other, right, and we would like to perform some simplification, right. What is a systematic way of simplifying the contour tree, right. So, that is the question we are trying to answer, right. Of course, if you have just a tree, right, one way to simplify the tree is to remove nodes, right, or to remove arcs, right, that will reduce the number of arcs and the nodes, right, directly. But this pruning of the graph or the tree should make sense, right. So, we would now like to do some simplification that is meaningful, right. So, let us take an extreme example, right, where I have something like that, right. So, what we are showing in the picture here is more extreme than what we saw earlier, right. So, you have a small bump on a big mountain, right. Let us assume that you are looking at this mountain from far away, you may not even see this guy, right, you will see only this, right. The question is, how can I go from here to here, right, in a systematic manner. You can imagine that this also happens at different levels. This could be a tree, right. Even so, this one will look like, I do not know, like this from far, right. How do I go from here to here, right. How do I simplify, right. With the contour tree, we actually have the necessary tools to go from one to the other, right. And say that again, please. Right. So, what you are saying is that you want to somehow remove local minima and retain global maximum, global minimum. That is the right intuition, but we will notice that there is some mismatch between that and what really happens in practice. We will come to that. Yeah, what is your comment? Good question. So, good comment, I think, right. So, what you are saying is, can I reduce the resolution of my data and somehow do the simplification that way, right. So, that is same as zooming in, zooming out, right. If you look at the same mountain from far away, you essentially do not want the hills, right, the small bumps, you want to see only the big mountain. That is exactly what we will do, but without some of the side effects of changing resolution or looking at local minima, local maxima only, right. For example, when you change resolution, that is what you would do when you let us say do blurring or something like that in images, right. It turns out that you can actually introduce new maxima or new minima. That procedure is not guaranteed to remove all the small minima, unfortunately, right. So, but what we will do, we will have theoretical guarantees, right, that all the minima which are small will get removed, okay. And the procedure is already here, right. What we will do is look at the contour tree and prune leaves one after the other, okay. The pruning procedure is a two-step procedure. One where you prune a leaf. So, in the example shown here, the leaf 80 is pruned. So, you remove that leaf together with the arc that is connected to it, right. Now, when you prune this leaf, you will introduce a new degree 2 node, right, because the leaf will be connected to a saddle. So, that the saddle will now become like a regular point, right, and all this makes geometric sense also, right. What is pruning correspond to? Pruning a leaf corresponds to taking this hill and suppressing it, kind of pushing it down towards the saddle, right. So, essentially making it flat. That hill became flat, right. That is essentially what you are doing. And so, this 50 now became a regular point, and you do not want regular point. So, you reduce that vertex, right. So, you merge across that degree 2 node, and you get a new tree, right. The new tree has the number of nodes and number of edges reduced by 1, well, number of nodes reduced by 2, number of edges reduced by 1. Does that make sense? Okay. Good question. It does change the characteristics, right? But you want to do it in a controlled manner, right? So that brings up the next question, right? So leaf pruning is a way to simplify. Fine, right? The question is, which leaf should I prune, right? Who damages the tree the least is the one that I want to remove first, right. So, here I want to introduce the notion of a topological feature. Each arc in this contour tree, we know that it corresponds to a cylinder, remember that, right. It corresponded to a collection of level sets, right, that was a cylinder. So, in this case, each arc here, for example, corresponds to this guy, right, or to this. So, here it will correspond to this, right. So, each arc corresponds to one of these features. These are called the topological features, right. I want to remove the topological features one by one, right, but I want to remove the low priority topological features first, followed by the higher priority topological features, right. And the way I can do that naturally is by ordering the leaves based on some cost associated with them. And what is the cost? The cost of an arc here is nothing but the difference in function value between the endpoints, right. If V1, V2 is the arc that I am removing, right, the leaf, if V1 is a leaf and I am pruning it, right, this is the cost associated with this arc, right. So, the difference in function value. So, in this case, this will be 80 minus 50, which is 30, right, and I will prefer to remove this as compared to this guy, because this will be 40, 90 minus 50 will be larger, right. So, I remove the smaller one, right. Does that make sense? So, I am introducing this whole notion of simplification via these contour trees, right. It turns out that this has very interesting connections with something much deeper called critical point pair cancellation, right, where you have all critical points, right. So, let us say P1 through P n are the n critical points of your function, right. There is a nice way to pair these critical points, right, such that each pair corresponds to a topological feature, right. So, this pairing is called persistence based pairing. Again, I am not introducing this, this is the more formal notion associated here, right. What we saw is an intuitive description which is sufficient for practical use. So, this persistence based pairing, right, of critical points is a way to go from the critical points to the topological features, right, and every pair, persistence pair, corresponds, has an associated weight, right, and that is called the persistence of that particular pair. And you can remove critical points in pairs. Remember, we cannot remove them individually, because if we remove them individually, what properties will suddenly start breaking? Can you think of any property that will break if I remove just one critical point? Remember some of the what you will suddenly start have degree 2 nodes, okay, but you remember some of the invariants that we studied, for example, the Euler characteristic. We said the Euler characteristic does not depend on the function, right. You are not changing the domain here, you are only changing the function. So, the Euler characteristic should not change, right. So, if you want a valid function after pruning, you cannot remove one critical point, you have to remove them in pairs. But can I remove a minimum maximum pair in for a 2D function, in this 2D function? Can I remove a minimum, that is also a pair, can I just remove it? How will that change the Euler characteristic? Will it, right, so the minimum contributes +1, the maximum also contributes +1. So, what does that mean? You have critical point pairs always have to be, one has to be a saddle, the other has to be a minimum or a maximum, right. So, you know exactly which pairs correspond to topological features, right. So that is the implication of all this, yeah. If you remove the global maximum and the global minimum, right, in this case it happens to be global maximum minimum, by the way it does not have to be global maximum minimum. What happens? You are essentially creating a function which is the empty function, right. You are removing the global maximum and the global minimum. So, how is your function even defined? So, you cannot really remove this final pair. You can remove, you will just change the topology of the domain if you remove it, right. If you want to retain the topology of the domain and still have a Morse function, right, then you cannot remove the global maximum and the global minimum pair. So, by the way, the simplification need not preserve the global minimum. There are cases where the global minimum can be removed, right, during the cancellation, right. I will talk about this example later during the break, right. I do not think it's a part of, it's necessary to talk about it now, it goes on a tangent, right. But the global maximum, global minimum need not be preserved during this cancellation, okay. Okay. So, in addition to this difference in function value based cost, you can have other costs, right. So, you can imagine that this cost here, right, this cost here corresponds to just the height difference, right, just the height difference. Now, so it does not really distinguish between cases where your mountain is not high but wide, right. Your mountain is not high but wide, right. You have a mountain like that. This mountain will be called a small topological feature as compared to something like that, right. Whereas, in some applications you may not want this guy, you may want to remove that, maybe because it is an outlier, right. The question is, how do you do that, right. So, the way you will do that is by introducing other geometric measures as costs. You do not want to use just the difference in function value. You look at, for example, the volume enclosed by this, or the area extended by this, right, at the base, right, and so on. So, there are ways to compute these geometric measures. One way to compute it is directly from the contour tree, right. So, this example may be complicated, but let us take the simple example. So, you can look at this example later when you see the slide, but a simple example is this, the same as what we saw earlier, right. How do I compute the volume enclosed by each topological feature, right? I know that the contour tree looks like this, right. So, the key is to start from the leaves and sweep inwards. Okay. So, I start from this leaf and the corresponding point here and sweep inwards. As I sweep, I look at how many points, how many regular points I cross, right. So, essentially I am trying to find the number of regular points that map to this arc, right. That gives me a approximation of what is the surface area of that feature, right. So, I am done with this. Next I sweep inwards from here. This gives me a sense of how many regular points correspond to this guy, and so on, right. So, this allows me to compute the geometric measures that I wanted to compute here. Okay. So, the point I am trying to make here is you do not necessarily have to focus only on function value difference, you can look at geometric measures also, right. And the last here, so depending on which feature you use, whether you use height difference or volume multiplied by the height, right, it is called hypervolume, you can get different simplified trees, right. So, this really depends on the application. So, in all these cases the original tree was very, very complicated, right, and here you have pruned it based on height or volume or hypervolume. Okay, fine. So, we will stop here.